Today we are going to discuss about this very important theorem, that is fundamental existence theorem for space curve. In previous PPT we have already discussed the intrinsic equation by finding curvature and torsion as function of S. Therefore it is quite obvious to know that whether converse is true or not. It means curvature and torsion as function of arc length S, can we determine the curve under suitable condition on Ks and tau s, and then we determine not only position of the curve in space but also so that all the curves congruent to it will have the same intrinsic equation. So let us look what is the statement of fundamental existence theorem for space curve. If Ks and tau s are continuous functions for all non-negative real values of s, then there exists a unique space curve determined but for position in space for which k is the curvature and tau is the torsion and s is the arc length measured from suitable base point. So let us first we understood what is the basis to prove this theorem. The method of proof is to construct the position vector Rs at any point on the curve and the moving triads Ts, Ns and Ds with the help of the given intrinsic equation already discussed. Now consider the following three simultaneous differential equation of first order in alpha, beta and gamma. That is obvious. d alpha by ds is k beta, d beta by ds is tau gamma minus k alpha, and d gamma by ds is equal to minus tau b. This is equation number 1, where alpha, beta and gamma are unknown function of s and k. K tau are given function ks and tau s. Now, since ks and tau s are continuous functions, the above set of differential equation has a unique set of continuous solution alpha, beta, gamma with prescribed initial condition at s is equal to 0 as guaranteed by the theorem on existence and uniqueness of solution of a set of differential equation of first order. The whole technique of proof is to use the three solution alpha I, beta I, gamma I, where I moving from 1 to 3 with three different initial condition and identify the vectors alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 constructed on the basis of solution with T and B. The set of equation 1 admit a unique set of solutions which assume the prescribed value alpha naught, beta naught, gamma naught at s is equal to 0, and let us consider alpha 1, beta 1, gamma 1 be one such solution taking the prescribed value. It means alpha 1 at 0 is equal to 1, beta 1 at 0 is equal to 0, gamma 1 at 0 is equal to 0. This is equation number 2. In a similar manner, we can find two more solutions alpha 2, beta 2, gamma 2 and alpha 3, beta 3, gamma 3 having the prescribed condition, that is alpha 2 0 is 0, beta 2 0 is 1 and gamma 2 0 is 0. That is equation number 3. And alpha 3 0 is 0, beta 3 0 is equal to 0 and gamma 3 0 is equal to 1 at s is equal to 0. The following four steps establish the theorem. Step 1. We shall establish the following properties of the above three solution, that is alpha square plus beta square plus gamma square is 1 and alpha 2 beta 1 beta 2 plus gamma 1 gamma 2 is 0. Alpha 2 is square plus beta 2 square plus gamma 2 square is 1 and alpha 2 alpha 3 plus beta 2 beta 3 plus gamma 2 gamma 3 is equal to 0. This is beta 3. Alpha 3 square plus beta 3 square plus gamma 3 square is 1 and alpha 3 into alpha 1 plus beta 3 into beta 1 plus gamma 3 gamma 1 is equal to 0. That is question number 4 for all values of S. These properties will enable us to introduce an orthogonal matrix for finding alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 and gamma 1, gamma 2, gamma 3 to define T, N and P. It means d by ds of this alpha 1 is square plus beta 1 square plus gamma 1 square may be written as 2 alpha 1 d alpha 1 by ds plus 2 beta 1 d beta 1 by ds plus 2 gamma 1 d gamma 1 by ds. Since alpha 1, beta 1, gamma 1 are solution of equation 1, so we get this expression, and after this simplification you will get here 0. Hence alpha 1 square plus beta 1 square plus gamma 1 square is constant. Using the initial condition 2, we get c is equal to 1, and so we have alpha 1 square plus beta 1 square plus gamma 1 square is equal to 1. In a similar manner, we can prove that alpha 2 square plus beta 2 square plus gamma 2 square is 1, and alpha 3 square plus beta 3 square plus gamma 3 square is 1. To prove the other relation in 4, let us consider d by ds of alpha 1 plus beta 1 beta 2 plus gamma 1 gamma 2. This is alpha 1 alpha 2. Alpha 1 alpha 2, it means on after differentiation we will get alpha 1 d alpha 2 by ds plus alpha 2 d alpha 1 by ds plus d beta 1 by ds beta 2 plus beta 1 d beta 2 by ds plus d gamma 1 by ds gamma 2 plus gamma 1 d alpha d gamma 2 by ds. Since alpha 1 beta 1 gamma 1 and alpha 2 beta 2 gamma 2 are solution of 1, putting for the derivative from 1, we may write this expression, and after simplification here also you will get 0. This proves that alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 is constant using the initial condition 3 t is equal to 0, so that this is 0. In a similar manner, you can write this expression 0 and this expression also 0. Now step 2 is we prove that t is equal to alpha 1 alpha 2 alpha 3, n is equal to beta 1 beta 2 beta 3, and b is equal to gamma 1 gamma 2 gamma 3 are three mutually orthogonal unit vector. And for this purpose, now consider the matrix A is equal to alpha 1 alpha 2 alpha 3 in row 1, beta 1 beta 2 3 in row 2, and gamma 1 gamma 2 gamma 3 in row 3. The sixth relation proved in the first step, so that the matrix A is an orthogonal matrix. This implies that if A dash is the transpose of A, then A dash is equal to identity matrix, where I is the identity matrix. Now the equation A dash is equal to I implies A dash is equal to A inverse, so that we have A dash dot A is equal to I. This is well known relation in matrix algebra. Now the matrix equation 5 may be written as this. This is the multiplication, you can say, the matrix R1 C1, and then after multiplication we will get this expression. Just to check it, multiply and check it. And now continue, this is equal to identity matrix 1 0 0. Now comparing the individual values, then you will get the following expression. This is equal to 1 and this expression is 0, this expression is 1 and this expression is 0, this expression is 1 and this expression is 0. The above six relations show that these are three mutually orthogonal unit vector t, n and p for each values of s. Now we will go for step 3. We find the position vector of a point on the curve. Let us define the curve as we know Rs is equal to 0 to s alpha s ds. That's equation number 6. Now differentiating with respect to s, we will get dr by ds is t, that is alpha s. This so that the arc length s and the unit tangent vector to the curve 6 are s and t, that is alpha s. Further, dt by ds is equal to d alpha by ds is equal to ks into b from 1. Since dt by ds is equal to k into n, we know that this unit normal vector n is a parallel to the unit vector beta, and k is equal to s if we take the sense of n as that of beta, then we get n is equal to beta. Now putting the value, since b is equal to t cross n, which may be written as alpha cross beta is equal to gamma, we have b is equal to gamma, and so dv by ds is equal to d gamma by ds is equal to minus tau s b. From 1, since dv by ds is minus tau n, we have tau is equal to tau s. Hence, if r is equal to s to st ds, then rs is the position vector of a point on the curve with the arc length s as parameter and having t and b as the moving unit trial, and k is equal to ks and tau is equal to tau s as curvature and torsion. We shall establish the uniqueness of the curve. To this end, we shall show that if the curve have same intrinsic equation, then they are congruent. Let C and C1 be two curves defined in terms of their respective arc length, having equal curvature and equal torsion for the same value of S. And for this, let A and A1 be two points of C and C1 corresponding to S is equal to 0. Now let C1 be moved so that the point A and A1 coincides. If T and B and T1 and 1 B1 refer to the curve C and C1, then C1 be suitably oriented so that T1 and 1 B1 at A1 coincide with T and B at A when S is equal to 0. Since different points of the curve are determined by the same value of s, and since both of the curve have the same curvature and torsion, so we may write d by ds t dot t1 is equal to t dt1 by ds plus dt by ds dot t1, which may be expressed as t into kn1 plus kn dot t1. Similarly, this differentiation n dot n1 will give you this n in bracket tau b1 minus k t1 plus in another bracket tau b minus kt dot n1. Now d by ds b dot b1 gives you b in bracket minus tau n1 plus minus tau n dot b1. Since the sum of the term of the right hand side of the above equation is 0, so d by ds is 0. Integrating the above equation, we obtain t dot t1 plus n dot n1 plus b dot b1 is equal to c, where c is constant. As s is equal to 0, t is equal to t1, n is equal to n1, and b is equal to b1, so that c is 3. Thus, we obtain t dot t1 plus n dot n1 plus b dot b1 is 3. Since the dot product of two unit vectors gives cosine, so the above equation gives the sum of three cosines. But the sum of the three cosines is equal to 3 only when each angle is 0. This implies that all the pair of corresponding points t is equal to t1, n is equal to n1, and b is equal to b1. Further, t is equal to t1 gives d by ds of r minus r1 is 0, which gives r minus r1 is a constant, say d. As s is equal to 0, r is equal to r1, so that d is 0. Hence, r is equal to r1 identically. Thus, the two curves C and C1 coincide so that the curve is uniquely determined except as to its position in space. This completes the proof of the theorem. Thank you very much. Thank you. Stay safe.